Good day, everyone. Thank you for joining us for day one of the two-day 12th annual HPC AI Advisory Council Stanford Conference. My name is Brian Sparks, and I'm the Director of Worldwide Operations for the Council and will be today's moderator. We have a robust agenda for the next 4 hours with great topics and speakers, including Microsoft, The Ohio State University, Georgia Institute of Technology, Stanford, and Peptologics. I encourage everyone to ask questions via the chat window, and our presenters will try to answer them after their presentation. This webinar is being recorded, and the sessions and the slides will be available on the Council's conference website over the coming days. I'd also like to thank our media partners, Gabriel Consulting, HPC Wire, Inside HPC, Intersect 360, The Next Platform, and Scientific Computing World for their ongoing coverage of the Council's worldwide conferences and activities. With that, let me introduce you to Gilad Shiner, Chairman of the HPC AI Advisory Council, and Steve Jones, Director of the Stanford High Performance Computing Center at Stanford University. Guys, welcome. It's great to have everyone here again. The floor is yours.
Yeah, thanks, Brian. Great to be online again. Hopefully next year we can actually be back at Stanford, physically on campus. You gave me, Brian, like 20 minutes to do a welcome. So because of that, I will let Steve to enjoy the full kickoff part, and then I'll do the welcome portion of the agenda.
Oh, the full kickoff portion of the event. I wish I had brought slides for this. That would have been helpful. But yeah, thanks, Brian, for the introduction. And Gilad, great to see you virtually again. So I am looking forward to 2023. And I believe we have that listed as to be confirmed in April. And I'm looking at some exciting new places to host it, and possibly with the lunch events at the faculty club. So that'll be a nice new portion to next year's conference as we welcome everyone back to the campus and we get back to in-person for the HPC conference. I think that's one of the most important things, is being able to interact with people in person, especially since we're in a user community here, made up of members of the HPC AI Advisory Council. So it's, the talks and everything are terrific, but I enjoy all of the interactions one-on-one with people, and all of the great friendships that I've developed with people over the past, what has it been now, Gilad? I mean, have we reached 15 years yet? It's been quite some time since we started off in the early days of this conference at, I think it was the Clark Center, maybe, where we had our first one, official kickoff, of the Advisory Council conferences here at Stanford. So, Gilad.
Well, you do have 7 more minutes,
Oh, 7 more minutes. 7 more minutes. How are we going to fill that time?
No, we can move forward if you want to, obviously. And I'm not going to take all the 20 minutes. So we'll start a little bit earlier with the sessions, and we'll have probably more time for the folks to present.
Mm-hmm.
So yes, definitely looking forward to go back on campus. And yes, remember being in several places, and starting many years ago, and looking forward to actually do that physically next year. So Steve, if no other things for the kickoff, I'll show some slides.
Sure. I think the only thing I'd mention really quickly is I do have a cluster building session that I'm going to be running monthly as part of this relationship we have with the advisory council. I'll probably engage Ophir and others in this, being able to just do a free session each month, a half an hour lunch and learn on how to get high performance computing clusters online quickly. So that'll just be it. We'll probably make some announcement on the HPC Advisory Council website and through that. But that's something that we're going to be kicking off here shortly. So it'll be a nice new thing through the education platform of the Advisory Council.
Sounds cool.
Yeah.
You also have the summer series coming up too.
Yes, that's true. We do have the summer series coming up, Summer Talks. And that's another one that we had started through the Advisory Council. And then, so we have a number of courses. We have ME 344, Introduction to High Performance Computing, 344S, the HPC AI Advisory Council Summer Series, where we have invited speakers that come in. I have CS 74, which is a computer science designation, but offered through continuing studies. The CS is for computer science, not continuing studies. But CS 74, Introduction to Building High Performance Computing Systems, which is an 8-week course. The first 2 were for matriculated students. The continuing studies course is open to anyone to come and learn more about building these types of systems. So we drop into anything from just building systems to workload managers, things such as Slurm, to containers, to Python, to just a number of different things that make up these clusters and things that you can use them for, even going into continuous integration, CI/CD work where you can drop those workloads onto your clusters too. So that's another great course to look into. You can find all of those at hpcc.stanford.edu. Maybe I should get a little, posting up on the Advisory Council site just to list those things. Every one of those classes has roots in the Advisory Council. Gilad, Brian, Sydney, of course, who is the orchestrator of all these things, have assisted me with starting all of these courses and promoting them. So it's just another great part of being a member of the council.
Yeah, very happy to participate with that. I'm more than happy to add to the website, Steve, when you're ready. The dates that the summer session starts is when?
June, mid-June. I think it's June 13th, this first week.
Perfect.
Yeah.
Okay. See, we filled the time.
Excellent.
Gilad.
Yeah. You can still take 2 more minutes.
Yeah.
Let me do this one.
Well, I can give a quick thanks to Sydney for the prompting, in the chat on the back end of, reminding me to announce all of these great things.
Yeah. Okay. So definitely thanks, Steve, for the collaborations and working together for many years, and obviously looking forward to continue with that in the future. 2 days, and we try to actually bring very interesting content that cover multiple areas in the world of AI or the world of supercomputing. Just immediately after me, a good friend, if Jithin allow me to call him a friend, a great friend, coming from Microsoft Azure, and he will have an interesting keynote on getting conversational AI innovations on Azure. We did together several sessions recently, part of some conferences on different capabilities that Azure can provide as a supercomputing cloud or HPC cloud. So it's definitely a lot of interesting things happening there. And of course, after that, Professor D.K. Panda from Ohio State University to talk about the progress on designing the middlewares for HPC and AI. And the second part of today, definitely interesting sessions on smart NICs and so forth. Tomorrow, Steve and I will have 5 minutes in the morning, and then another great set of presentations from Gregory Kurtzer. Edison will talk about the market trends, where HPC is moving. After that, sessions from NASA Ames, and ending with Mike Houston from NVIDIA to talk about building. I think it's the number 6 supercomputer on the top 500 list. So hopefully you will enjoy the topics. Do encourage discussions, which could be done on the chat. And I'm sure that if time permits, Brian will enable also to do discussions, real-time discussions, and asking questions with the speakers. A little bit of the council. I would assume that most of you knows about the council, but just a quick recap. The council mission is to bridge the gap between AI and HPC technologies and its usage. And as part of that, we are conducting several conferences around the year and around the globe. Last 2 years it was online around the globe, but we do hope to go back and start back with the physical conferences starting the second part of this year. There's a lot of things that we're doing as part of the council, a lot of activities. Just mentioning a few of those. One is establishing, or one is the cluster center that we established that includes multiple infrastructures that include different kind of technologies. The recent one also includes data processing units, or DPUs, and which enable entities to actually create new software packages. I'm sure that DK Panda will talk about the Mvapich GPU that enables to actually migrate operations of MPI to run them on the network, and he leveraged the system at the council for doing the development and doing the testing. Access to the systems there are free of charge for members of the councils, and membership is free. So it's essentially a no-brainer. Another part that we're doing is creating best practices, different kind of application, different kind of workloads, providing information on the impact of different kind of hardware setting and software frameworks on the performance or the scalability of different kind of workloads. Everything is published on the council website, so you're more than welcome to check it out. We are very proud to manage some of the student cluster competitions around the world, and definitely be part of the Stanford summer school, which will start in June. The ISC student cluster competition, which is happening, actually it's happening now, but we'll have a physical portion that will be part of the International Supercomputing Conference end of May and beginning of June. So that's coming fast, and we're happy to get back to actually a physical competition between university teams in Germany. After that, we will manage the Apac student cluster competition that will happen online this year, and we'll take advantage of a couple of supercomputing centers around the world. And of course, the RDMA programming workshop that will also happen later this year. We're proud of those activities. We're proud to manage the competition and proud to take part of summer schools and the programming workshops as part of enabling students or enabling universities to get more into HPC, get more experience, hands-on experience, and more courses. Conference-wise, we did the Japan conference early this year, which was an online event. We did this WINS one, and now we're doing this in Stanford online. We do hope this summer and autumn, the one in Australia and then UK and hopefully China will be a physical conferences, or at least a hybrid conference. So part of that, it will be online and with a physical presence. So for more information on the activities, joining, access to the cluster center, you can find on the website. Anything that you would like to ask us, to suggest and so forth, of course, can use the email address or join the LinkedIn group. So with that, I definitely want to thank Steve for the operations and working together. I also want to thank the speakers that will speak today and tomorrow. It will be definitely very interesting sessions. And I do again encourage everyone to ask questions or even to do the drill time and verbally ask questions at the end of each presentation. So with that, Brian, I'll give you 13 minutes back, more or less. And it is actually my great pleasure to ask Jithin to get his slides ready. And again, great friend of mine. We've been doing several exposures on technology-wise recently and presented in different conferences. I'm looking forward for the keynote. Jithin, thank you for joining us today. And the stage is yours.
Good morning, all, and thank you so much, Vlad, for the warm welcome. So today I'm extra proud and privileged because I got the friend of Vlad title. So that's great. Cool. So let me start. So I'm hoping like the screen is visible and all. Is it okay?
It's perfect.
Cool. Thank you. So let me. So the overall title is breaking the barriers for HPC in the cloud, right? So the overall outline is so we want to start with what are the good things about HPC in cloud? What are some of the core challenges for HPC for people like moving from say traditional HPC like on-prem to cloud? There are like a lot of performance and scalability concerns. Because when we started initially, there were like a lot of performance concerns, right? So we'll go over most of the core challenges there. I would like to go over some of the Azure HPC designs, say how we try to attempt to mitigate some of the concerns, and then offer like the best performance and scalability for the end workloads. And of course, like along with some data points, right? So performance and scaling results, and also some of the latest rankings that Azure has made, and then finally, we'll conclude with right? So that's the overall session, overall outline for this talk. So let me, without any delay, like we move to the next session, next topic, right? So HPC in the cloud, right? So traditionally, like when the cloud was started, right, mainly it was for say web servers or HPC was never in the context when it was initially started, right? So people always had the concern, what will be the performance? How would be the variance be, etc. Right? But there are a lot of good things for HPC in the cloud, right? So you can cut down a lot on the cost. You can always say get an on-demand HPC cluster, right? So for example, if you want to run a particular job, then you scale up the set of VMs that you need, again, the set of VMs that you really need for that particular job, right? So sometimes you may need GPU, sometimes you don't need that, sometimes you just need compute, sometimes you need compute plus IB, the fast network. So you just spin up the VMs that you really want, and you only pay for what you actually use, right? So there is, unlike say traditional, say on-prem clusters where you, always have this cluster and you have the overhead, say of maintaining the cluster, you have to take care of the utilization, etc. So that's all good things about it, right? And when you go to the say cost factor, right? So you always have, for the on-prem side, you always have the initial cost. Then so so once you have this cluster, you're maybe stuck with that for a very long period of time, right? Say of years. So you have to work on the maintenance. You have to for example, the operational cost. You have the cost for say, after the 5 years, you have to decom the assets, etc. So a lot of overheads there also, right? But on the other hand, like cloud, you just use those VMs only when you need it, and then you only pay for what you really need at that time, right? So those are some of the plus minus there. Again, when it comes to cloud, right, there is almost zero maintenance, right? So there is no need to take care of the hardware. So sometimes you may need to say do some software maintenance, right? So for example, if you want to upgrade certain kernels, upgrade say move to a new different drivers, etc. So those kind of minimal maintenance are there, but again, it is depending on the usage model. Sometimes you just want to use the latest VM image that the cloud provider provides, and which may have all these later kernels, etc. So the maintenance on the cloud aspect is much lower, right? And also you don't need any refresh, right? So you just go to the cloud when you really want it, right? So you don't have any baggage of the old infrastructure, etc. Right? So that's another plus point. I think the main one that I really like is the HPC for all concept, right? So traditionally, all the say HPC centers or supercomputers, it was only certain say groups or set of people will have access to it, right? So but when you have HPC VM access on the cloud, right? So anyone with literally anyone with an Azure subscription can go and access the VMs and play with it, right? So these are not say traditional older generation VMs, right? These are really up-to-date hardware. For example, just to give an example, so when Milan processors came out, right? So Azure had VMs on the same day that that AMD announced Milan processors, right? So it's you have access to cutting edge technology, right? So same with the network infrastructure also. So those are some of the pluses, I think. That we can give with say HPC in cloud. Of course, this may not be the full set of pieces, but the things that really stood out, right? So that's it. And so let's take a look at what are some of the core challenges that that we see, right? So these are all the good things HPC on the cloud can provide, but there are still some really solid concerns, right? So people have seen performance variability, right? Traditionally, for example, like you run this application once and then at a later point you run it again. So you may not, you are not getting the same performance, right? So those are still very valid concerns. And like sometimes it can happen on the on-prem cluster also, but again, on the cloud, it is more susceptible, right? So that's definitely one concern. And I'll go over like each of these in detail, but just to the high level overview. So another one is the performance isolation, right? So on a shared, this is actually running on a shared environment, right? There are multiple tenants or multiple customers using the same cluster at the same time, right? So there can be impact. So we'll see, how we solve some of those these issues using the latest IB technologies, right? So we'll go into those. Another one is say difference in software environment, right? So people really want to have the same software environment that they are familiar with on the cloud also, right? Say, for example, the same set of MPA libraries or the same set of communication libraries, so they want to use it here also. And the other one is, the data movement overheads, right? Sometimes you have like really large amount of data, but what if like you want to move the entire data to the cloud, right? So those are some of the concerns. So let me focus on each of these a little bit, and then we can go into like say how Azure addresses some of these concerns, right? So let's start with performance variability, right? So as you all know, right, the VMs are running on a host, right? So you can always think that okay, there can be say some variability or some aspects of the host that can impact the workload, right? So there could be say agent rollouts that are happening. For example, like there are multiple agents in the host, like maybe like coordinating on different aspects, or there could be like say a host doing some operations which are triggered by the VM, etc. Right? So we need to have like good isolation from the host activity. So that's definitely one thing. So just to highlight how the impact or such an activity on the say on the VM, right? So this graph on the right. So we have say 3 bars here. First one is say host is idle. So it's, for example, the network is or the network interface is exposed over say non-SROUV or traditional approach, right? So we can see that okay, the peak bandwidth that we get in this approach is say about like 60% of the peak. Now on the same note, like say if you induce some host stress, again we can see that okay, the performance is now degraded to about say 30%, right? So again, but it is much, like about 30% of what we can get from the peak, right? So, but on the third graph, right? So in this case, the host is fully busy, but like say if you expose the NIC using say SRIOV, right? So you are still getting about peak bandwidth, right? So these are some of the designs that we go to achieve those independence. But again, I'll go into details. But just to give an overview of say how a host stress can impact the actual performance. So that was the motivation here, right? So that is one aspect. The second aspect is say, even in the VM, right? There are multiple different agents running, right? Say, some of those could be like, not specific to say cloud environment, for example, the kernel, agents, etc. Right? But there are say cloud specific ones such as the monitoring agent, like say which captures the CPU activity or the network activity, etc., and reports to say portal or some reporting system, right? So you can always disable that, but again, by default, some of those could be enabled, right? Another one is guest agent, which assists you in say, for example, the remote operations, such as say if you want to get serial console access, or you want to like say change some of the configuration on the VM, etc. Right? So to coordinate those things, right? And those things can have slight impact on the performance also. Especially for say CPU sensitive applications, and it can cause say some like memory or cache pollution, and could be very well visible in the VM, right? So those are some of the concerns. So I'll go into detail how we address these things, right? So that's the first set of challenges. And the second one, yeah, so this is a good example, right? So this is the need for network performance isolation. So this particular experiment we ran, we did together with NVIDIA, I mean, of course, with the help through GitLab. So I mean, this graph highlights two different applications, LAMPS and Incopact 3D. So it shows the leftmost one shows say if in the cluster there is no, it is completely isolated, right? So it's so you're running the applications X number of times, and you're plotting the performance as a histogram, right? So I mean, we can see that there is, almost very little deviation, right, in the performance, and most of the times it is hitting the peak performance. Now, on the second graph, for the same application, like we induce, say, congestion, right, synthetic congestion, using the different congestion simulators in GPCnet, right? So we can see now, oh, okay, so now the performance is all around the place, right? So so this is an example where, okay, like when you have multiple external customers or external tenants doing different network activity, how what is the impact on the performance, right? So the same story for Incompact 3D, right? So in the third graph, that is the strict isolation one, and again, like with GPCnet, right, you can see the performance is much different, right? I mean, it is all over the place again. So one thing to note is that so this is not completely specific to, say, a cloud environment, like even on a shared cluster, right? A cluster which is, like, say, managed by Slurm or PBS, and then multiple customers like running, or submitting the jobs, they can also see similar issues, right? But in the cloud, the one difference is that, like, as a customer, you are not able to see what all other jobs are running, right? But on a bare metal cluster, like, you can still see, okay, the other jobs, how many jobs are running, etc. So you may have some visibility, right? So that's one thing. Again, like, we will see down in the slides how we address this, and how some of the IB technologies or IB designs are actually addressing these problems, right? So we'll go into that. And the next one that I mentioned earlier, like, it is the software environment. So, for example, many most HPC users, like, they want to use the same software environment that they are familiar with, right? So whether it be HPCX, MFH2, OpenMPI, MPH, like, all the libraries that they are familiar with, right? And they can incorporate, like, similar kind of optimizations or, like, tunings that they have identified on-prem for the particular applications, and they want to apply the same things on Azure or on the cloud also, right? So that's a very reasonable, like, requirement, right? So just to give an example, right? The HPC Advisory Council, like, we have, like, identified different tuning configurations for the different applications. So some of those things can be directly applied on the cloud also, right? They want to apply on the cloud, right? So without having to retune it or anything. So that's one thing. And again, third one is that, say, even on an on-prem system, they may be having a particular set of say software libraries that they have created as an image, and they may want to, like, bring them to the cloud, right? So same things. They want to do, right? But on the other hand, like, say, some cloud solutions may need, like, say, some custom network libraries or some custom versions of MP libraries, right? So it may need some longer setup time or longer ramp up time, or even, like, say, specific help from the cloud vendors to, like, say, really optimize it, right? So those are the things. Those are, again, some of the challenges, right? So okay. And the last core challenge that I see is the data movement, right? Like we discussed, say, for example, your actual data center, your on-prem data center is in East US, but say, what if your cloud is cloud cluster is in, say, West US, right? So, the data locality, that becomes a concern, right? There can always be you can always pick a different cluster in East US itself, but again, you have to be careful about the data locality. There can also be some, say, security concerns, right? Say, while moving the data or while, say, permanently storing that in the cloud, right? So there are those concerns. So in this talk, right, so I want to focus on the first three, because the last, the data movement is kind of say logistics, etc. But I would really want to focus on the first three, especially focusing on the performance and scalability aspects, and see how Azure addresses these concerns and give the best performance and scalability, right? So let me quickly move to, before moving to the actual design, so just an overview of the different cloud, say, data centers, right? So, these are the different Azure regions or the different clusters that we have. So typically I used to get the number of regions, etc. But it's changing so vastly, so I dropped that. But this is a quick overview of the different clusters. So as you can see, it's truly global infrastructure, and again, with compliance, data resiliency, etc. And then of course the multiple lines of service availability. And again, with competitive pricing also, right? So let me quickly move to the technical stuff. So, okay, so if you consider the different VM types, right? So specifically for HPC, so you can broadly classify them to two different types, right? So the H and the N. So H is traditionally specifically focusing on, say, traditional MTI type applications, where you have say high compute and high memory, plus fast networks, which is of course most widely used one, say, InfiniBand, right? So that's the H series SKUs. And on the other side, N, which is the GPU VMs. Specifically, again, those can be divided into two, depending on the usage. So the visualization SKUs, that's the NV, and then the deep learning or AI SKUs, that's the NC or ND, right? So those are the main classification. And I really want to focus in this talk, really want to focus on the SKUs with InfiniBand. So those are the ones that I underline, the HPC SKUs, HB, HC, HBv2, HBv3, etc., and NC, ND, etc. Right. So the main characteristics are, say, how we can identify this based on the SKU name. So if the SKU name contains an R, then that means that the VM supports RDMA. And one interesting or one good thing that is that we always support only one VM per host for the IB-enabled SKUs, right? So the main design factor was that, say, for these VMs which has IB, so it's mainly for applications that are scaling out, right? So anyway, if you want to scale out, right, then why not start with the full node itself, right? So that's why we always sell one VM per host for all IB-enabled VM types. And the IB is exposed to the VM using SRIOV. So that means that, so it's full host bypass. And also full feature support also, right? So all the different features that we are familiar with on the bare metal, all of them are available on the VM also. And again, so we have say it's a single cluster, but there could be multiple customers, right? So how do we prevent the different one customer from accessing or interfering with the other customer, right? So we use IB partition key. So every deployment will have a different P key, right? So they will not be able to communicate across between each other, right? So that's the main idea. Going on to say how you address some of the performance variability, say, from the host, right? So just to highlight that, right? So I want to show the design of one of the H series VMs. So I picked the HPv3. which is one of the latest SKUs in the H series, right? So H series is actually Milan-X based VM, which is the very latest AMD processor, and again with our HDR 200 gigabits per second IB. So 64 cores per socket, and then 2 sockets, right? So that's the 128 cores for the entire host, and then one CX6 NIC, right? 200 gigabits per second HDR. So here you can see that for every socket, so we take 2 cores per NUMA, right? So 2 cores here, 2 cores here, 2 cores here, and 2 cores here, right? So let me get a pen if that's possible. Yeah. So 2 cores from every NUMA node we take out, and we restrict that. We restrict the host to those 8 cores. So in the Windows hypervisor, there is something called min root. So we can specify that, okay, these are the set of different cores that the host can use, and all the host activity is restricted to that to those cores. And similarly, right? So for all the rest of, say, 30 cores here, 30 cores here, 30 cores here, so 30 per every NUMA node, right? So those we create another group which is called the CPU groups. Again, one of the Hyper-V features. So with this min root and CPU group, you establish a strict partitioning between the host and the VM. So the host will only access these 8 min root cores, and the VM will only access the remaining 120 cores, right? So that's how we attain performance isolation from the host. And then again, IB is exposed over SRIOV, right? So this VM, in the spec, it is, let's say, Milan-X, 120 cores, as we saw, like 30 cores per NUMA node. And it has an impressive L3 cache of, say, 1.5 gigabyte and 448 GB memory, and then again 200 gigabits per second IB, right? So there are different configurations on how you can expose the VM. So sometimes maybe because of the licensing restrictions, sometimes they want say only few number of cores per CCD exposed to the VM. So you can, depending on how they want, how the customer want, we can expose the cores per CCD. But again, in all the cases, there is only one VM per host, right? So because it's IB enabled. Another design, another example design. So this is, one of the N series VMs, which is the NDV4, Indeed for the AI deep learning workloads. So again, this is ROM-based VM, ROM-based architecture, and then 8 CX6 NICs and 8 A100 GPUs. So with a total, network throughput of, say, 1.6 terabytes per second. So here also you can see X number of cores are taken out from each of the NUMA node, and you restrict host to those cores, and again the rest of the cores we form a group, the CPU group, and then expose to the VM, right? So the GPUs are exposed through DDA, and the NICs are exposed through SRIOV, right? So it's completely host bypass. So we'll show some of the performance results of these two VM types in the coming slides. But this is the overall design on how we offer the performance isolation from the host, right? So this is again so with min root and CPU groups, right, and the SRIOV, how is the performance variability, right? So on the left side, this is MPA random access on a single VM, right? So we can see and run for maybe say around 500 different runs. You can always see that the number is almost exactly the same for all the different runs, right? So very little variability. I think it was about 5%, which is similar to what we see on a bare metal node also, right? So and again on the right hand side, open form for about say 50 different runs. And you can see like the end application number is very much uniform, right? So there is very little, or there is little performance variation between the runs. And again, so this is a similar benchmark, right? So in this case, like we induce stress to the host and say, I measure the nickel performance on the left side. So we can see like it's 8 process and 16 process, like say 1 and 2 nodes. So you can see with and without the host stress, there is no impact on the end performance, right? So that proves that okay, with host stress, like there is no variability for the end workload. And on the right-hand side, these are actually Superbench. Many of you may be familiar with the Superbench. It's a new framework to evaluate AI supercomputers. It's a mixture of, say, different benchmarks, starting from the different, say, micro benchmarks, say CPU, GPU, network, etc., disk, etc., and then all the way to different models, right? The training models. So in this case, we ran Superbench on a VM, and then in the host, like you induce a synthetic stress. So all the host cores were 100% HPC using a synthetic CPU stress utility. And then you can see that, okay, with and without the host stress, we plotted the relative performance. So with and without the stress, the performance is very similar, right? So this kind of proves that, okay, this design can achieve uniform performance. And about the network features, right? So this is even more interesting. So as I was saying before, like we have different generations of SKUs. So HB, HC, and DB2, these are our previous generation, which is running ConnectX-5, 100 gigabits per second IB. And the newer generation, or the current generation, is HBV2, HBV3, and DB4. Those all are running are with CX6, ConnectX-6 IB adapter, right? So 200 gigabits per second, and this is the really cool part of it. So since we are exposing it through SRIOV, right? We can offer all the different features that we can get in bare metal, right? So DCT for really scalable workloads, hardware offload, like the traditional HCall, and also say hardware tag matching, then UD-based multicast, Sharp. Again, like this is restricted to some clusters, but again, like you have you can now like do Sharp on cloud. Dynamic routing, like the different, say, congestion control and adaptive routing features, more reliability with Shield. And also an interesting part is that our clusters are all factory topology. So, and then with no oversubscription, right? So none of the public clusters have oversubscription. So that's another good aspect of it. So no oversubscription plus adaptive routing, that gives you the best, like peak performance, right? So that's another good thing. And in the next session, right, so we talked previously about like the software environment. Like, in a cloud, like people want to use the same software environment that they are familiar on the on-prem. So, so in order to facilitate that, so we have certain, say, optimized HPC VM images. So currently we have the CentOS based HPC, Ubuntu based HPC. So these have the different, like IB or different InfiniBand based MP libraries, communication runtime, like different HPC libraries all built in together. So, a customer, when they come to Azure, like they can just pick this particular VM image from Marketplace and then deploy VM. And they're actually good to go, right? So they can start. So there is almost zero ramp up time, and the good part is that these are the exact same MPI libraries that that folks are familiar on the on-prem system also, right? So that's another good thing. And there are like periodic refreshes on of these images also, so you always get the best and latest software runtime. And so we are by no means restricting to these images, right? A customer, if they want to bring their own image or their own, like they want to bring build on top of this image, right? They have that flexibility also. So this is something that customers can take advantage of, like just to get like really fast ramp up time, right? Okay, so now this is the more interesting part. This is the performance and scaling highlights, right? So just to start with the MPI performance characteristics. So for the different H series, right? So this is HPV3. So here we have our favorite OSU latency bandwidth, bidirectional bandwidth. You can see that on HPV3, we are about, like, say, 1.5 microseconds, and then peak bandwidth of about 24.6, so which is very close to the 200 gigabits per second, right? And then bidirectional bandwidth of about like 49 gigabytes per second. So very close to the theoretical peak there, right? And similarly, like this is NDV4 MPI characteristics, GPU to GPU in this case, again, using OSU micro benchmarks. So here we can see about, like, say, 2.43 microseconds, and then again, very close to the peak bandwidth, right? So similar to what we, very similar to what we can get on the bare metal clusters also, right? And again, like, GPU direct RDMA, like all the cool features are supported, right? So GPU direct RDMA being one of them. So here on the first diagram, I'm showing the RDMA, pure RDMA IP right bandwidth number. So all the 8 NICs, they are getting very close to the 200 gigabits per second number. And again, on the downside, like the plot down below, so it shows the GPU direct RDMA. Again, we're getting about, say, 195 gigabits per second for each NIC and each NIC's GPU pair, and all of them getting the number simultaneously, right? So that's another thing. Since like we are offering through SRIOV, right? So there is no need for any custom runtime or library or anything. Like, so any GDR capable MPA libraries or software runtime, like, it can all be supported on Azure, right? So that's another good thing. And again, like we talked about Sharp, so these are some of the Sharp numbers. So this is a nickel on 8 nodes. So the blue line here, which is Sharp disabled, and then Sharp enabled, we get around 257 gigabytes per second. And then with without Sharp, like, it is very close to the peak number, like 200 gigabytes per second in this case. So in the effort to enable Sharp on Azure, right? So so we did many of the work together with Mellanox, and we improved on the UCX-based Sharp AM, Sharp T communication, because that will be in a cloud environment, we want to make sure that goes through a secure channel. So that's done, and then there was also some optimizations on the Sharp tree initialization, etc., and also the Sharp AM, Sharp T connection keep alive, etc. Right. So and also GRH support, because on the cloud now we can really scale out and to multiple thousands of nodes, right? So that was another scaling improvement. And this is another interesting benchmark result. So this is the congestion control feature available on the HDR, and then also the newer generation ones, and it's getting better and better. So this is some evaluation using GPCnet. I know, like, I'm sure, like, all of you are familiar with that. So as you know, like, so first you run the benchmark without any congestion, and you run with congestion, and then you evaluate the congestion by using a congestion factor. Like, so basically, how good it performs with and without congestion, right? So that's the congestion factor. So ideally, like, if the performance is the same, then the congestion factor is 1. But if it is higher, then that means your performance is dropped because the number is the number is much higher now this time, right? So so these are like three different benchmarks: latency, bandwidth, and all reduce, and two different configurations: CC disabled and CC enabled. Right, so we can see like with CC disabled, okay, right, we can see there is a lot of impact, right? But with CC enabled, you can see it's almost 1. So there is again like some outlier, but again like not like the case where CC is disabled, right? Same story here for the bandwidth. So here also very close to the 1 number. And again, for all reduce also, right? So this is, I mean, very critical in like any shared environment, like whether it be bare metal or cloud. It becomes more critical in cloud because I mean you don't have like visibility onto like what are the different workloads that are run on the cluster, etc. Right? But you can clearly see that it improves on the congestion and also improve the tail latencies, right? So this is still experimental on here, but I mean, like it is as we work closely, I mean, we clearly see indications of like this getting much better and optimized in the next generations, right? The next one, again, the same kind of evaluation on the end application. So initially, when we were discussing the challenges, we saw these two graphs, the first two for the different applications and how it behaves with condition, right? Now, I wanted to show the third column here, right? This is with the congestion control and then how it behaves as compared to the initial version, right? So we can see now it is very much similar to the case where there was no congestion at all, right? That's really nice thing about the congestion features in InfiniBand, right? So we are getting really close to really close performance to us, as we are running on a perfectly isolated system. So yeah, and another benchmark result, another experiment here. So this is the impact of adaptive routing, right? So this is one case where, so this is actually a case, interesting case that we found at Azure, right? So when you're running a setup, the benchmark on a setup or the application on a set of nodes, the performance was really bad, right? And then you change the order, then all of a sudden the behavior changes. So we analyzed it and then found out it was actually due to congestion, right? So like what the same link being used for a single direction. So just to give an example, right? So this is an nickel all reduce where it forms a logical ring. Say so host A, B, C, D forms a ring, right? And depending on the static routing, right? So we map the static routing through the actual NICs, etc. So we see that, okay, when we map the communication, it was like, say, host 2, when it wants to communicate to host 3, so it goes to IB13, and then because it was at position 3, and then goes to the corresponding top of the rack switch, and then goes to this this host here. Similarly, from host 3, when it wants to connect to 6, so it goes to IB16 because it's at position 6. So this was the destination-based routing, and then from here, so 2A to 2B, right? And similarly, 3A to 3B, 4A to 4B. So we can see that, okay, 1A and 3A are again on the same link and the same direction, right? So whether if it was in the reverse direction or the two direction, then it would have been fine. But in this case, it's the same. So we could see that, okay, the bandwidth on this particular link, like we measured every link, right? And this particular link was cut into half, right? So, and we saw the same impact on the end workload, right? Say about 50% of the peak. And when you enable AR, right? So you are getting the close to peak performance again. So because with AR, like you're spraying the packets in multiple different links, and then you're not hitting with this issue, right? So that's why we are able to get very close to the peak in this case on the same set of nodes. More details are here. And like on the adaptive routing, like depending on the SKU, it is enabled on different SLs. More details are mentioned in this blog. And quickly, because of time restriction, I'm going a little faster towards the end. Quickly on the scaling efficiency. This is the Milan X results. So this is again the AMD Milan X, the HPV3 VM types. So multiple different workloads, and Fluent, race car model, and then also combustor model, and then OpenFOAM, right? So one of the nice things about Milan X that I like we discussed earlier is the really large L3 cache, and also they have some adaptive like caching designs in there. So you can really see the scaling efficiency as you hit past that L3 cache size, right? So so you are getting really nice scaling efficiency on multiple different workloads, right? And one of the other highlights, I didn't put a graph here, but so Azure, like in Azure, like for the HPC workloads, we have scaled to even around 85K cores. And I think like this is by far the largest that we had seen on like say different public clouds. So other clouds, are stopping at much lower core counts, but we have scaled to like about 85 cores, and again like the scaling efficiency was still holding up really nice, right? So that was another nice thing about it. And quickly about the rankings, right? So I just want to showcase 3 of the different rankings. So MLPerf, we had a submission last December, and it was our first submission, and we got like rank number 2, and it was of course like number 1 for the public cloud. And again, like I'm not going to super details here, but more details are in the link. Again, on the top 500, rank 10 in last year SC's ranking list. And these were both using the NDV4 VM instances. And again, all powered by 200 gigabits per second IB, right? So, and again, the third one, Graph 500, this was the previous year SC time. So rank 17, this was again the first submission in Graph 500. So HPV2, we got rank number 17 in Graph 500 list. So quickly, so overall conclusion is that we discussed like the different challenges, and then we saw how like what are the different designs that we saw to avoid these kind of things, and then we saw these performance and scaling results, and how this is actually not impacting, or how Azure solves those kind of issues, right? And it is quite visible in the different rankings, top 500, Graph 500, or MLPerf results. So clearly, like we can see that cloud, supercomputer on cloud is actually getting real. And the main highlight I would say is that with clouds, HPC is now available for all, right? So I think that's another key point that I wanted to share in this talk. So with that, let me conclude, and I also put like some of the pointers and like more data points, etc., results, etc., in the different blogs. So thank you, and we can take any questions.
Great. Thank you, Jithin. Appreciate the presentation. Now it's a good opportunity for everyone who hasn't submitted questions. They can do it, hopefully through the Q&A window. You can also do it through chat. Whatever easier for you. We'll be monitoring both. I do have one question. Is adaptive routing available on Azure, or is it a technology preview at this point?
Oh, it is available. It is available on Azure. Yeah, on all the EDR and HDR SKUs, right? Those are the two ones where it is available, right? From the hardware. So in both of the SKUs, it is enabled. So it is just that, so there are two different types, right? So the H series and the N series. So the H series, so we haven't enabled it in the default SL, but any non-zero SL, so for example, SL equal to 1 or SL equal to 2, all of them has adaptive routing enabled. And the reason why we did not enable in the default SL or SL equal to 0 is because some of the MPA libraries, they have some strict assumptions on the order. So we wanted to like eliminate those kind of issues and say enable, for any user who really knows, okay, say this particular MP library supports, can work with AR enabled, so they can really take advantage of it. And on the N series, it is enabled by default on the SL0, the default SL, because most widely used runtime that we see is the Nickel, and it supports AR really well. So it is enabled by default on that.
Okay, thank you. I currently don't have any questions in the queue, but if they come up, I'll certainly forward them your way so we can get those answered. Jithin, thank you so much for keynoting this conference. Really appreciate it.